So I want to define derivatives now. What I will do is take a function from open interval of a norm matrix, norm vector space. These two will be norm vector spaces. We have some two different norms and there are two different spaces, and it will look something like V W, and it will map vectors over here to vectors over there. So I need to define derivatives. What I can do is go to a point here, call it P, and I go in the V direction and try to take the directional derivative in that direction. So I will compute f of p, and there will be some f of p plus v, and whatever happens to that f of p plus v, and the limiting condition of v tending to 0 will be our directional derivative. So I will define the of p is defined as limit of h tending to 0, or I will just change every v to h of v, p plus hp minus f of p divided by h, and then h will tend to 0. So this will we what is this operation? This is the vector space operation of w, because f is a function that's going to w, um and these would be elements of v would be element of any element of this guy, any element of u, because v is a direction. V can be any direction in the vector space v, but P has to be in the domain. This is U. And because it's open, I can go in any direction. That's the point. That's the reason we need open domains for differentiability to work. Now, there are funky business with the V here, which I will show. But the right hand side, if the limit exists, then only it is defined. Otherwise, it's not defined. That's known. Um, Otherwise, you can do what you can do is this. Okay, so funky business happening with the directional derivative. So this is called the directional derivative. So if I go in the v direction and the limit exists, and if I want to go in the v2 direction, limit might not exist. Let's say if I go in the alpha v direction, what would be the change? I mean, they shouldn't change at all, but because the direction shouldn't matter, but we don't have a way to rectify that yet. We have to just check what happens with this definition. So I will just write whatever happens for the alpha v version. Um, Alpha v at the point P, it will be f of P plus alpha v times h minus f of p, and you take the limit h tending to 0. Then what's obvious that we can take a alpha here, and then we can take the condition that alpha h tends to 0, which just this make this h dash, which makes this quantity the directional derivative in alpha, in v direction at the point p, and there is a alpha coming out. So they are the same except there is a alpha coming out, which is okay-ish, I guess. We can just take the norm of v to be 1 and then take the directional derivative, I guess, to know whatever happens to the function, because I shouldn't it shouldn't matter what view we are taking. We should be able to look at that direction and ask in that direction how is the function changing. This is the major motivation for directional derivative. The direction should matter, not the how much fast you are going, I guess. But it does matter how much fast you are going. If you're going the v speed, if you're going alpha v speed, something quote unquote speed, there is nothing we can physically mean to be speed here. But it is much more weirder that it satisfies another condition where if v1, v2 directions, in v1 and v2 directions, the limit exists, then this quantity will look something like limit of h tending to 0, f of p plus hv1 plus hv2 minus f of p divided by h, and we take the same limit. But what happens is, if I repeat this again and take something like f of p plus h v2, then what happens is I can just consider p plus h v2 as some p dash, uh, and then p dash will go to p or something like that. But we can recognize that this is directional derivative with respect to v1, because this is the thing that is added here, plus limit of h tending to 0. I added this, I separated this term, I have to add this term, and this is the same exact thing but for v2. So not only the scalar multiple comes out, v1 plus plus splits apart. So it is linear in this slot. The direction matters only linearly, varies linearly, matters linearly. So there's a this slot is linear for every point p. This is odd. I need to go to a deeper understanding to understand why is this coming to be linear. And the second problem with all this is only partially true. This is the partial derivative. I wouldn't know that if the function is totally differentiable in all direction or something. That is one of the important criteria for to define differentiability of a function of this form. So what I want to do now is take a different route. Maybe we took a directional derivative, which looks certainly like this, but the notation is very which is just goes in v direction, sticks at p. But if we want to do something else, maybe you can take a curve and then do the same thing. So I will take a curve here in the domain vector space, and it will go to the other vector space, and I will compose that gamma, which is a curve here, and f composed with gamma will be a curve here, and f composed with gamma would be a derivative, of the function f at in the direction of gamma dash t at the point gamma. And we will see that and we can also prove this theorem that these are the same thing. Gamma dash direction, in the gamma dash direction, the function f at the point gamma of t behaves exactly the same as the answer would be exactly the same as this guy. So our curves is giving us a new handle to uh, work with it, that if I go faster on the curve, the answer of the derivative will be larger. This is giving us a actual physical significance of the scalar multiples. But v1 plus v2 is splits apart. That's a very weird phenomenon to happen. Maybe we can figure that out by devising something where total means in totality of direction. I don't know where the actual terminology comes in, but totality of direction makes sense. That you want to take all the directions together, not just single one. So if I want to take all the directions together, I have to take some function, a function that goes from v, so all the directions, this is all the directions to w, and this should be approximating the function at that point or something. This should be the first order approximation. Um, the approximation should look something like first order and linear, maybe. So what we are doing is we are taking a linear approximation, so that there should be some TP. I should take a better example, better name, but let's say there should be a linear function called AP, where f of p plus v would be approximately same as the function evaluated at p plus ap of v, and the actual equality should be something of this form. There should be the difference, the error term should only be in the order of v. Like it should only matter how much distance I'm going away from v. This distance, that should be the uh, margin of error, something. But I don't wanna emphasize on error analysis or something, because these are actual um, these are, you can make them proper. And the way to make them proper is if I divide everything in this equation by mod of v, but this does not exist yet. I mean, we are considering this might exist. Um, if I divide everything by mod of v, and then ask the question, what happens is if the mod of v goes to 0, that error term should go to 0. So I want something of this form. For something of that form to exist, I would ask the question, for p belonging to the domain, if there exists a AP, which is a linear transformation, and I would write it as a linear transformation from V to W. So this is the set of all linear transformations from V to W, and I would just say if f of p plus v minus f of p minus that AP of v, norm of that divided by the norm of v should go to 0 when I take the norm of v tending to 0. If that happens, I would say AP is a linear transformation that approximates the function f at the point p, and I would call that AP the total derivative of f. It would be a linear transformation that takes v directions to directions in W, I guess, or not exactly. It would take the v to something. We don't know yet what it would take it to. It would we have to compute the actual linear transformation for a fixed point and then actually compute it. But I would just state a theorem without saying it, that we have come full circle. There's a theorem which says if in this definition of a total derivative, the total derivative is just a linear approximation, a linear transformation that approximates the function at a point, dp of f, if it exists, it might not exist, uh, of a vector v would be the same as partial derivative of v at the point p. So because this slot was linear, and we have also shown that this slot was linear by definition, this is a linear approximation, and this slot was linear because we proved it. If it exists, it has to be linear. This theorem makes sense that they should work out because we defined two different things, but we define sort of the same thing. Approximations should be same as derivatives. That's that, that that's not a theorem or something. That's the motivation of theorems to work on about. Okay, this is actual theorem we can prove. Um, the note catch here is dpf might not exist, but derivatives, partial derivatives in some direction might exist. So we will call a function differentiable if and only if dpf exists at a point. So this has to be like something like a